originally I did this presentation, I used PowerPoint so I can do animation, but it's PDF, so we'll have to deal with it. And the biggest downside is I had 2 slides with animated with Dilbert, who's my favorite consultant. So we'll just have to deal with that. Okay, what I'm going to do is spend a reasonable number of slides on the foundation notions of why I think we should be doing 128-bit addressing the way I'm talking about it. We're going to go back to the 70s and see how a lot of the technology and thoughts go back to the early 70s. We're going to talk about exascale. I really want to build the world's fastest computers, but if you can't program it, they're irrelevant. So ultimately, I'm going to show you how this dovetails into designing the world's fastest computers, have a proposal. You're going to see a lot of references. This is almost sufficient to be a paper. So let's look at the background. If we go back to the late 70s, and a lot of this I've been personally involved with. The PDP-11 went from 16 bits to 32 bits. I should have added that, and then DEC went from 32 bits to 64 bits with alpha. And every time they increased the address space, they added, it was a different instruction set. Data General had the MV series from 16 to 32 bits. Spark, HP RISC went from 32 to 64. Intel tried to avoid going to 64 by doing Itanium. I was somewhat involved with the Itanium project. IBM, 32 to 64, ARM, etc. And the key thing is memory management and protection were intermingled. And the major motivation for this is you needed to address more physical memory. So that's when Moore's law was still valid. And in those days, we used to say, I was responsible for the Data General machine. The best benchmark is the one your competition can't run. So if I can do A of I, and my A of I is 64 bits, and your A of I max is 32 bits, you lose. Very simple concept to get across. But other people tried to say, let's do something else with the address bits. And I give you 3 references. One is IBM. FS, which is IBM's attempt to do this, was a 16-byte, 128-bit pointer with capabilities. And it really never saw the light of day, but a diminutive version of it became the IBM System 38 AS400, which of course is now actively selling. Data General built a 128-bit machine, a unique address. I was the co-lead on that project and still have scars on my back. And Intel tried to do something in the same vein, Intel 432, where they had 80-bit UIDs, a lot of other stuff. So we have a lot of history in the past of what worked, didn't work, etc. The other things that happened is we had 2 major projects from research. One was, of course, Multics at MIT. And a lot of people don't realize that Unix is a diminutive of Multics. That is, what we found out that was overboard, too much, ultimately became Unix. And at UC Berkeley was the Genie project. But what happened is, in a lot of graduates, new era of computing, the technology was not ready. I can certainly share with you that in the Massachusetts area, within 495, 128, all the major computer companies, the operating system was loosely based on Multics, and all the people who developed it came from MIT, etc. So let's go forward. Now, I believe designing computers and architectures is an art. So like art, there should be certain objectives on what you're trying to do. And we'll see what this means later on when I talk about exascale computing. And the key here is program generality is the ability to move a program between computer installations, etc. That is, if you have to, you want to recompile, but you don't want to have to restructure. You want things to be as general as possible. And generally, the things that are as general as possible are the things that are accepted. Oh, I do have my one Dilbert. So, and of course, because it's not animated, it doesn't show it. Okay, the first one, this came from the version 2.1, page 105. There's only one mistake that could be made in computer design that is difficult to recover from: not having enough address bits for memory addressing and memory management. What's covered here on page 105 is a comment that Krista told me he put in that basically said, architects will argue forever and ever how to expand an address space, and ultimately they'll decide on the simplest thing of just adding more bits. I think that's a correct paraphrase. He's shaking yes. So I always use Dilbert as a way of keeping myself sane. And if you look at the middle pane, it says the goal of our organization is to make security procedures so inconvenient that you give up hope and die from bed sores. Now, 10, 15 years ago, that may have been relevant. But if today that means, as we heard Eric Rose talk about, you protect your company from going under or losing money, we have to come up with what's the right compromise between, let's call it inconvenient security procedures, using the right cable, as we found out, to plug in the phone from Google. But RISC V, the last pane, is perfect. We take pride in being independent from the companies that fund us. So you're in the luxury of doing things that you believe is technically correct and not worrying about theoretically what the members, the platinum members, gold members, etc. So let's see what this means. When I went to school, virtual address meant the address that referenced your disk. It was what was attached. Remember, a virtual address doesn't reference main memory. A lot of people don't realize that. It references disk. And that's why we have things like TLBs and everything else. But in the last couple of years, from a network address, the networking people have created a 128-bit address, IPv6, where nominally, and please give me some leeway on this, half the address is the name of who I'm going to, and the other half of the address is some information relative to that entity. We live in a world of uniqueness. MACs and URLs are unique. Email addresses are unique. Phone numbers are unique. The real problem I see is in security is that we have too many independent security domains, and we have to write software to bridge them all from client to server and back. There's no one consistent model. There's nothing to do with addressing, but it's just a model to be used. So the question I pose is, what if one unified name structure could be developed? What are the objectives? This is a paper written by Butler Lamson in 1971, and it's relevant today. There are two basically seminal papers in protection mechanisms. Butler's paper of 1971, I'm not going to read it, but you can see it's just as relevant today. We want to have protection to avoid modifying another user's program, copying, degrading the service another user gets. Today we would call it denial of service. Perhaps the most seminal paper in security, it was in 1975 by Schroeder and Salzer from MIT. And the key here is the objective of a secure system is to prevent all unauthorized use of information, a negative type of requirement. Usually always take a positive type requirements. Every access to every object must be checked for authority. This principle, when systematically applied, is the primary underpinning of the protection system. So that goes back to the simplicity of what we're trying to do. Previous efforts, the first one is from IBM. It was Radin was the chief architect of FS. And again, a unique integer was assigned to everything that was created. Again, it goes back to sort of the notion of IPv6. The next three things are patents on two things that Data General built, what was called the FHP project. And then Eric Rose talked about the Sherry project at Stanford, which is a capability-based product. The first capabilities that I know of came about by Fabre, who came out of Berkeley, that was published in July 1974. So basically, we have a whole history going back beyond the birth date of the majority of people in this room. That's the interesting thing. The foundation was set many, many years ago. Moving up in time, in 1974, the people at University of Washington, UW, created an operating system called OPAL. And they were talking about, can I have a single address space for all applications? Persistent pointers. People began thinking of what if an address addresses things over the network, not just what's attached to an I/O cable. And you can read what they say in the third bullet. That for all time in a single computer, it's enough for a small network, 64 bits, but not enough very long on the global network. So I'm going to keep coming back. Do we want a global reference, not just a local reference, to be persistent? So here's my straw man for RV128I. It's 128 bits. Object ID is 64 bits. Byte offset is 64 bits. Now, I only have a half an hour. I've done a lot of work on this, so I could probably talk for 3 hours if I had to. The object ID is a unique identifier. And all it means simply is a software or hardware structure that is considered to be worthy of a distinct name. I'm not telling you what type of name, it's just a unique name. Indexing A of I is 64 bits. But in the context of RISC V, the program counter stack pointer, which is called the CI format, is 64 bits. So when I index the stack, when I get the next instruction, I don't go into another object, I wrap around. If your object for instructions is more than 2 to 64 bytes, you have the wrong program. The other benefit of this is that this is ISA independent. It's like routing IP packets. That means if this becomes a standard, you can have the Power 128, God forbid the x86 128, all dealing with the same pointer. And that's an example of what Dennis means by program generality. It's general enough that the ISA can work with any of these pointers. And protection and memory management are independent. That's very, no matter what's determined, that's very important to separate those two. Why do we want this? Again, I say better security. You know, that's a catch-all phrase. I don't believe we want 120-bit flat addressing. We want simplified sharing. We need authentication, revocation, etc. What is an object? You could see there, it could be a PCAS, for those who don't know, means program, partitioned address space. It could be blockchain. Today, blockchain is a universal ID to do things. The creation of an object is a central name server. Usually when that comes up, people get, oh, we can't have a central name server. Well, if you go to the net, if you do URLs to DNS, that's a central name server. That's what blockchain is. We live in a world of central name servers resolving things. And the question is, should an object be an IPv6 address or not? Nominally 15 months ago, Krista and I had a very long discussion on this. And I can spend an hour giving you the pros and cons. So for now, what I'm going to say is, subject to further discussion, maybe I'll take bit 63 of the object offset and say, if it's 0, it's an IPv6 address. If it's 1, it's a unique name. It's a placeholder. What about access, control, and domains? Later, Ron Minnick will talk about his threading approach in his operating system. You hear about rings in there. He talks about things in ring 0, ring 5, etc. Rings are hierarchical in nature. Sometimes that works, sometimes that doesn't work. You really want something that's not the case. So in my case, in this case, I would propose that we have a domain-based system and we have a very hardware-mediated domain crossing and return. Again, I can go into the details. We don't have enough time. Authentication, we heard that. The most important thing in security, one of the most important things is, are you really Steve Wallach? Are you really Ron Minnick? Are you really Patterson? Because if not, all bets are off. So we have to spend a lot of time understanding this. And with respect to the global access control list, we really have it today. Adobe and Microsoft each has their own 2D slice of that. When I say, give me Word or give me Adobe Writer, Adobe has, for Steve Wallach, I'm allowed to have that. So we really actually have that today. Each company is a 2D slice. So therefore, an example using Adobe, and I'm not trying to pick on anyone, is Adobe can execute my domain, it can read and write the file system, but it can't execute in a different domain. So if I don't trust Adobe, I can put it in a separate domain with limited capability. That could be called the sandbox or other things. And of course, to be consistent with contemporary thought, we don't want to run Flash. Memory management is separate from protection. Every object has its own memory structure, page tables, hash indices, etc. And I didn't have a chance to put this on here, but now with the new type of memory, non-volatile memory, the notions of a page fault that we know for the last 40 years changes. What does it mean when you take a page fault when the access is a couple of microseconds, not a couple of milliseconds? So that has to somehow be factored in when we do this. And each object can also have object size for constraint checking. So now I'm going to deep dive. One of my Unix kernel gurus said, this is a reasonable machine state model for 64-bit Linux as it exists today. And if it's not right, someone tell me, but we have a proc ID called prid_t, 3 basic tables, and basically each table is unique for each process, and those things are mapped into system-wide resources to manage the disk cache, directory cache, page frame cache. So in essence, in today's Linux, we have a 96-bit virtual address space, of which 32 bits is the proc ID, virtual address space is 64 bits. And base just says, how do I get into a page table? How do I look at the 64 bits? And ultimately, I get a page offset. And each implementation can choose to associate on a 96-bit namespace or 64, and you purge the TLB. So if I have 128-bit addressing, my object ID is typically hashed address space, but I have, from day one, a system-wide address space. And I go through the same thing to look it up. The DOE, when they look for procurements, they like to have 1 byte per peak flop. And Exascale is 60 bits. And the more physical memory you can reference, the better off you are. But this physical memory is never on one node. It's distributed across 10,000, 100,000 nodes. So here's my example. This is matrix multiply, in essence, written in a language called UPC. Looks pretty simple. It is. And there's underlying hardware to do that, because the address space supports it. I've actually built this, not like this, but a smaller version. So one of my axioms is the machine that's simplest to program wins. User cycles are more important than CPU cycles. So in terms of generality, and I don't mean to pick on it, where I typically speak at supercomputer conferences, and Bill Dally is next to me, I always bring up an example of doing this in CUDA, and I quote that we don't know what pornographic programming is, but when we see it, we know it. So that would be a good case in point of something that's not general, not portable to something other than an NVIDIA architecture. I'm not saying that's wrong, it's just an example of that. So virtual address space, data referencing, get object ID byte offset. Now we have a very sophisticated access control list. The access control list has 3 dimensions: source, who I am, who I'm referencing, and what domain I'm in. Within that entity is typically access control list entry, permissions, local reference, global reference, object length. Protected subobject is in hardware do something that a sandbox does. So we can isolate things. So I can say anything I download, even from email, goes to a protected subobject that has only read reference, no write reference, or can only use a certain amount of CPU time, things like that. A typical ACL entry, again, you can read it. I'm going to say it again, this is all in hardware. There's no software. Just a month ago, in the last issue of ACM, Roger Shell produced a nice article, 3 pages. I know Roger for a long time. Those who are old enough know that he was the author of what's called the Rainbow books, and in particular the Orange book. That defined what a security kernel is. And when we took regular BSD and made it a secure level, 95% was documentation, 5% was changing the code. in terms of audit lists and things like that. And I think the most important takeaway here is this notion of a reference monitor. This is the entity that has to be trusted. And I saw later on there's a paper from some people from MIT on Sanctum, which talk about their version of a reference monitor. I looked at it, it's an excellent paper, and I look forward to their presentation. So the summary, it's to deal with virtual addresses from 2020 and beyond. It's the notion that a virtual address doesn't reference local, it references across the network. So when I want something over there, I don't want to have to FTP it. I don't want to have to do whatever else. I want to just say, index it or read it. Okay, it does show the summary from Dilbert. Probably you can read it, but the PowerPoint slide could change our entire company strategy. The rest of the industry would have to copy us, and that could change the entire world. I think that's what RISC V would like to do. But of course, the last pane is the best one. Someone has been having delusions of effectiveness. Okay, there's lots of references here. There's 18 references, and I spoke in New York speed. So let's take questions. Thank you.
Thank you, Steve. Any questions for Steve? Thanks for everybody getting back in here after the break time. We're right on time, and we got 3-4 minutes for questions.
No question.
We're running out of gas.
I built the machine out of gas, gallium arsenide. We don't want to do that.
Boom, boom, boom.
Right. Thank you for leaving there. I could have taken, well, if we don't have questions, let me show 1 or 2 other things then.
Okay.
Okay, backup slides. Eric Rose talked about, last thing about Sherry capability. One of the things when you have to do is how do you revoke someone's privilege? How do you say, you're no good anymore, I'm not going to let you get to my database? So, you know, it could be a timeout, like if you go to a banking site, your local bank, if you don't do anything for 15 minutes, they shut you out. So if it's a access control list, it's easy. You go, you don't have access to Microsoft Word anymore because Microsoft owns that 2D slice, and you're done. Capability is more difficult because there's no central name server. So if you want to look at papers on capability, which have tags which say, this is a memory reference that's protected as opposed to data, you should read the Fabry paper, and Watson is the Sherry reference that's been done at Stanford and SRI mainly, but other people. This is my funny thing, is that with watches now having network, maybe the way we'll do exascale computing is by tying our watches together using IPv6 running code. The other thing that we can actually do, even on current machines, I'm constantly amazed by how many times people have to scramble their stack to prevent people from overriding it and banging a bad return address. You can actually create the following in hardware. I have 2 stacks, what the user sees and what the system provides. And so the user visible stack is on the right, the real stack is on the left. So when you do a return, you return from the shadow stack, not from the user stack. So all these attacks that try to change the return address to go to a bad place doesn't work because you can't reference on the left. And I read that Intel and Microsoft are working on something similar to this. Whether it actually sees the light of day, I honestly don't know. Okay. We have a question? Oh, wow.
Are you familiar with IPFS? And if so, where do you see an address space ending and a Merkle tree beginning?
Actually, I'm not familiar. What is IPFS?
Interplanetary file system. No joke. So they want to.
Is that the thing that VinSurf is working on?
I don't know. I don't remember who's working on it, but
Okay.
it's turning the world into a hash table addressed, self-verifying availability of blocks. So kind of a cross between Git and Tor and what's the other one?
No, I apologize. I vaguely remember reading something about it, but
I mean, it ties into the security questions. If you can't trust the network and you want to get memory accesses over the network, how does that work?
okay. Well, if it's interplanetary, does that mean we have to worry about what the Martians are doing, or?
Not yet.
I'm sorry, I don't know.
We can talk about it in break.
Okay.
Thanks, Steve.